Sorry for the little delay. We're still working out the webinar issues. Anyways, I would like to welcome Jonathan Beaudoin. He joined CCOM in the spring of 2010. He has a PhD in geodesy and geomatics engineering from the University of New Brunswick, as well as bachelor's degrees in geodesy and geomatics engineering and computer science, also from UND. Here at CCOM, he's been carrying on in the field of his PhD research, which is estimating sounding uncertainty from measurements of water mass variability. But he also plans to work with oceanographic databases and also underway sound speed sampling systems and geocoder. So I will turn it over to you.
All right, thanks. Welcome everyone. My first seminar here is an official person at CCOM. I gave one a while back before I decided to move down to CCOM, so it's nice to be on the other side of the fence. So I'm not going to read the talk title there.
Click on presentation. That's right.
There we go. So this is a slide I use in quite a few talks introducing this idea to people. We work in a busy ocean. There's a lot of temperature and salinity variations. It's a very interesting place to work. And we like to think we're doing a great job of working in the ocean with seabed mapping. We think we put an awful lot of effort into getting highly calibrated sensors and aligning them perfectly and knowing where they are to the nth degree on a vessel. But at the end of the day, we're still shooting sound through a highly variable water mass. So even despite our best efforts to engineer the best survey platform, there's the big problem of getting that sound through the variable ocean environment and back. And the temperature and salinity variations that we see that are natural patterns in the ocean refract with the laser on this. Refract our ray paths from the sounder to the seafloor. And if we don't account for that, we end up with sound biases and uncertainties. And so we work really hard to have perfect instruments. We still have this problem. We have to deal with the ocean. And it sure would be nice if we could put some efforts into understanding how to deal with the ocean before we got in the field. For example, could we know a tough spot to work in from an easy spot? An easy spot is an environment that the ocean water is so well mixed that the temperature and salinity are the same everywhere. So the speed of sound is the same everywhere. And we just multiply our time measurements by that, and we get a range measure. So it would be nice to work in those environments, but we don't always have that. That's not always available to us. Instead, we work in complex estuaries, for example. Here's this surface salinity in Chesapeake Bay from the, I like this, the CBOFS, the Chesapeake Bay Operational Forecast System. And this shows us how the salinity is varying over a tidal cycle over a few days. And this is complex. This might be a difficult spot to work in. There's a lot of spatial change and temporal change in the salinity patterns. But if we jumped up to this next arm in the estuary, this is boring. So we could look at this map and say, well, this is probably a tougher spot to get good, accurate data. This one's maybe not so tough. So the trick is, could we somehow, ahead of time, before we get in the field, identify where the tricky areas are, where the easy areas are, and could we figure out maybe the tricky stages of the tide or the easy stages of the tide and understand what's driving that variability and then work around it instead of just showing up in the field and hoping for the best, which unfortunately for the most part is what most of us end up doing. So how can we study an area to understand that variability and then in turn appreciate how it affects our data accuracy? And that's what I really want to talk about today. How can we study an area? I could ask around the room. We could look at local knowledge. Maybe the fishermen know of certain tidal patterns, current patterns that could be useful for us. Don't go out there on a rip tide, but that sort of stuff. We could look at real-time measurements from buoys. We could look at archived measurements from oceanographic databases. The math model that I just showed you, that could be useful. We could hit the books and start reading on some oceanographic papers in the area that we're going to work in, or maybe just take some remote sensing imagery. All of these could be used. They're all valid approaches, but they're all pretty qualitative and subjective. We could look at this map. here and decide, we just did that in the last slide. This is probably an easy area, and that's a tough area. How tough is it? Should I worry really hard about the sound speed or just a little bit? We need some quantitative tools. And so my approach is, if you want to study an area, maybe you should go out and take some of your own measurements. And really what we want to know is what's driving the oceanography, the temperature and salinity conditions. That's what we're trying to understand. What exactly are we looking for? Well, we're looking for challenging oceanographic conditions. If we could jump out and do some pre-analysis to figure out, are we going to have a tough time getting good data or an easy time, we want to find these challenging spots. And this is a definition I just cooked up. A challenging oceanographic areas where water masses exhibit complex horizontal or vertical spatial structure and or a high degree of temporal variability. So we need instrumentation that can capture that. We need to be able to sample rapidly. If you're on an ocean-going vessel doing the traditional oceanographic CTDs, where you take it out of the shed, go put it in the water, let it go down for an hour, bring it back up, and then put it back in the shed, go to the next station, do this over and over and over. This model of sampling the ocean isn't really going to work for us. In estuaries, you can get away with a small boat and hand lowering a CTD, but still, you're limited by how fast you can lower it, how fast you can do it up, and then go to the next spot and study your area. If you want to get a good picture of what's going on, you need to be able to sample rapidly. And that is what we're going to talk about today, is using the instrumentation to rapidly sample the water mass and then turn that into information that's meaningful to us, the hydrographer. So I'm going to walk over a few tools that I like to use in this sort of problem, and then sampling methods. How should we use those tools? When and where should we sample? And then how should we take that data and then turn it into information that's meaningful to us so we can make survey-based decisions. Then we'll look at a few case studies of data sets that I've acquired in various spots around the world, and then finally wrap up with looking at some of the field work I have planned for this summer. So tools first off. These are underway files. It's rapid sampling. We want to capture spatial variability over time. So these are moving pixel profilers. It's easier to see in this one. A large winch, and then a line that hangs over, and then a token with oceanographic sensors on it. And then you basically let that go up and down the water column and measure things. And we'll see on the next slide. There's expendable bathythermographs, underway CTD, which is a similar idea as this, except it's much more manual. And then this one I think is kind of neat. Fishing rod and a cast. But these are options that allow us to how fast we can reel that back. Here's a couple of videos. This is from the Beaudoin Ocean website showing how the MVP system works. So the towfish free falls and is winched back up. And the real-time controller takes an input from an echo sounder that tells you how deep the bottom is and how fast the vessel's going, and it makes decisions on how much bait to let out and when to put in the drum and when to winch it back up. You can do that over and over and over. The underweight CTD is the exact same principle, except it's manual. So a person is deciding when to release the probe. And this is a little video right off YouTube. And there's a person with a stopwatch, and you know how deep it is, and you know how fast the boat falls, and you let it fall. It's driving on it, and you hit the brake, and then you push the retrieve button, and it sucks it back out. And so it's the same principle, except this is all controlled by humans, all controlled by electronics and software. But they do the same thing. They allow you to get casts at a very rapid interval. In shallow water, you can get a cast a minute. So depending on your vessel speed, you can get casts every 90 meters up and down the next. High resolution oceanographic sections very quickly. For those of you who've gone out and CTDs, it's hard to get that kind of data in a short period of time. So, well, this is how I use it, and I think I just learned it. Because start to go out to St. Rod and run the MVP system on our launch all day long. We did 800 or 900 casts in one day. and have these beautiful oceanographic data sets. And so this is just an example from this model here. We zoom in, might pick a start spot and an end spot, and then go back and forth all day long, letting those underlying much data as possibly can. This isn't exactly the scale, but it's an example. We might get stations where the blue dots are, and that corresponds to, if I have time here, my distance from the blue dot. As I get more samples, I'm going away, and I'm at the red end. I turn around and come back, and I get more on that section. And I've done one section down and up. And I do this over and over over the course of a tidal cycle, because maybe we know that the tide is what's driving the oceanographic variability. And if I look at this, I could grab all of the data for a common distance, like that, and that would give me a temporal subset for that small location. I could grab a slice of data here and treat that as a spatial subset collected over a very small time interval. So I have a dense data set that allows me to look at how things vary spatially, temporally. There's a few assumptions and limitations here. The spatial subset, we're trying to approximate an ideal oceanographic array which would have sensors hanging in the water column sampling simultaneously at the same time to capture a true spatial snapshot. How is the water varying spatially? But because we're moving through that water, we're sort of modulating the temporal effects as well. So you need to keep these sections short. You can't run up and down the river and have a 6-hour section and then expect that that slice of water that you're looking at is tied to a certain stage of the tide. It's not. So if we keep the sections short, maybe 30 minutes, we can say something about spatial section being loosely tied to maybe high tide or low tide or rising tide. The temporal subset, what we're trying to do is approximate a fixed mooring in one location that's logging data continuously throughout the day. We're not doing that. We're going back and forth up and down the line. And depending on the currents and the person at the helmet, or even the person who's telling them where to go, it's kind of hard to hit that exact same location every time. So we're not going to, unless we go through a lot of effort. So it's not quite the same as having a mooring that's fixed in one location, logging data all day long. But we're approximating that. So there's some limitations to this, and I hope to flush these sort of things out and how they affect the analysis through the work here. So here's an example of some real data collected just up in the port of St. John in 2008. So we have, I don't know, a dozen casts or so. So I've got sound speed versus depth, and then temperature versus depth, and salinity versus depth, and then a temperature salinity plot. And this shows how that water mass changed over the course of 9 hours. And in that same data set, grabbing a spatial subset over a 5-kilometer section, which was acquired in 30 minutes, we see very different patterns. So we could look at this picture and say, it seems to me that over 9 hours, there's more stuff going on in the water than there was spatially over a 5-kilometer section in 30 minutes of time. So we could make some decisions, and that's a subjective decision. We might decide to run long survey lines because the spatial variability is low, but the temporal variability is high. But that's subjective. We're looking at graphs. We need a way to turn this into something that's meaningful to us. And that brings me to my next point. We need some analysis methods. We have sound speed profiles here collected off of Bank Row Bank. And we're collecting every 3 or 4 or 5 minutes. And there's an awful lot of variability in the water. And that's basically making our acoustic rays bounce and bend in all sorts of different directions. We need a way to tie this data that we collect to the information that we need. This is what we need as a hydrographer. How does this affect my sounding uncertainty? And once I know that, I can appreciate whether this is good or bad, or something I should worry about, or something that I don't need to worry about at all. And so that's what we have here. And this came out of my PhD work, was how to take sound speed profiles and then turn that into something I can understand as a hydrographer. And really it comes down to looking at ray path diagrams instead of sound speed profiles. So for each of these, the green, the blue, the red sound speed profiles, I have equivalent ray paths. And what I can look at is the divergence of the rays, or the dispersion through the water column, and that gives me numbers that I can understand. The red ray is shallower than the blue ray. I would have a positive depth bias, for example, and I would know how much that is. So I can do that for a chosen depression angle or travel time. I can do that for any, oh, sorry, here's another example of some real data. So I think probably about 90 sound speed profiles collected over 2 hours in Rotterdam. Here's the ray path diagram. For each one of these, there's a ray path, and we can see it. At the bottom, there's quite a divergence here. We're looking at half a meter or so. So I can take that, the end of the ray paths, treat it as a point cloud and compute a mean position, yellow triangle. The same, and then along the same lines, I can compute standard deviations in depth and horizontal. And there are the numbers that I need, those standard deviations. This is nice. It tells me that there's variability. This tells me whether I need to worry about it or not. So now I can understand what this means, and now I can start making some decisions. So if I can look at any depression angle and any travel time, I can look at all depression angles and all travel times from the sounder to the seafloor and across the whole angular sector and come up with this wedge lookup table that tells me as a function of depth and angle what the uncertainty is. And we can look at any portion of this here. I can look at how the uncertainty grows with depth of the outermost beam. So I could look at here, this red uncertainty profile. I'm very certain near the sounder, and as I get deeper and deeper on the outermost ray, I get more and more uncertain. I could look across the swath. I'm mostly certain here, and then I have greater uncertainty here. So that's this section here. I could also just look at one number here. If I had to boil this entire image down to one number to do some statistics with, this is the one number I probably want. It's the outermost beam. That's where we feel the refraction problems the worst. And that enables me to do some statistics. I can also simplify that for real-time viewing. If I take this image and boil it down to whether or not the data would meet a specification that I'm trying to meet, for example, IHO order special 1A, 1B, or 2, I can color code that. And now we've got this boiled down to a simple metric. Just like every other sensor that's on our survey platforms, where there's a green light when it's okay and a red light when it's not. And when it's a red light, you do something about it. Now we've got the ability to do that. We can take the sound speed profiles and make decisions. We can realize that most of my sector is within specification. The outermost portions maybe not, so I can't plan on being able to cover all the ground that I did. So maybe I should change my line spacing, for example. So here's a little animation to show how we might visualize this in real time. If I have sound speed profiles changing through time, so a thermocline gently rising, so there's just a plot and I just spread it out in time, I can compare my first cast to my second cast and come up with this wedge display. And I can do the same over and over and over. And that's one way to visualize this. We can see that the uncertainty is greatest between these three casts, 1, 2, 3. That's when the rate of change is at its greatest through the water column. And then up here, it's not changing so much. What I can do is visualize this. The moment I get cast 4, I have good information. The moment just before I get cast 5, the refraction solution's at its worst. So I can visualize this with a perfectly okay wedge, and then this one, and interpolate in time and in depth, and come up with this display. And this is a display that I end up using quite a bit in my real-time software that allows me to assess these things in real time. And the software I use is something I cooked up for my PhD research. I call it Soundscape. It lets me see the landscape of sound, so it just kind of made sense. I've got sound speed, temperature, and salinity profiles versus depth, a TS diagram, a geographic viewer, and then most importantly, a time field viewer, which has time running along the x-axis and then depth here. Every time I get a cast, it's a line, so the blue one or these green ones. I've got tide down here. And what I can do is start to visualize the water mass that I'm working in. Instead of having just a bunch of green lines, I can color code a sound speed or salinity field here and see that I've got salt water, brackish water, and fresh water, and that's changing through the tide cycle. So at a high tide, I've got a bunch of salt water underneath me, but at a low tide, it's mostly fresh water. And I could start to color code that using that visualization technique into a field that makes sense to me as a surveyor. Again, green is good, red is bad. So this is a pretty picture that's meaningful to oceanographers. This is a picture that's meaningful to surveyors. I can see I'm getting a lot of red at certain stages of the tide here. At other stages of the tide, I'm getting a lot of green. So maybe with this high density data set, I can start to see that maybe surveying on a rising tide is not that great of an idea if I want to have good data. But coming around on a falling tide and a low tide, my data quality is much better. I don't have all those reds in there. I can also take that same water mass there, and if I had used this first cast for the whole day, what would this water mass look like to me in terms of sounding uncertainty? And that's what this visualization is that same idea, except interpolating across all of the casts. So the first cast of the day would only do you for a little while, and then most of the time afterwards it wouldn't be any good at all. So we can start to ask questions like, well, what's the optimal spatial sampling rate and temporal sampling rate? So that's the tools, the methods, and I'll just take a drink of water. Now I want to look at some of the case studies in various spots around the world where I've managed to collect an awful lot of MVP data. So I'll start off with the Rotterdam Waterway in the Netherlands up there. This was done in 2009. And it's important to point out that this particular port is surveyed 13 times a year. There's an awful lot of sediment being dumped in there. It's probably the largest, busiest port in Europe. So that's not a good combination. They have a channel that they need to keep dredged to a certain guaranteed minimum underkill clearance. They've got a pile of sediment. And unfortunately, it's a very, very tough spot to work in to be a hydrographer. 13 times a year, you've got to go out and slog through this sort of mess. This is a salinity section from A to B over 23 kilometers. So here's the salt water, the fresh water from the river, and the turbulent interface between the two. And this just goes back and forth all day long. And you've got to do that and survey this whole place 13 times a year in a very challenging environment. And people that do that, is Sema here? He's not? Okay, I'm going to try and say it. I think it's Rijkswaterstaat. He would have corrected me if I said it wrong. It's the Dutch Public Works. The people that do the surveying go out and have the job of doing that work, but the refraction is a real limiting factor in the area. So they work with these dual-headed systems that shoot to 150 degrees, but really they can only use a small chunk of that because the refraction is such a big problem. It forces very close line spacing, so very inefficient surveying. And really, if you're doing this 13 times a year, if you could survey slightly more efficiently, if you multiply that by 13, so a little bit of savings on one survey adds up quickly in terms of costs of surveying that. And what they wanted to know was, could better technologies or methods solve this refraction problem here? They have a challenging area to work in. They want to see, could we choose some different technology or try to work a little differently? And so I went over there to give them a hand. They wanted to know, they wanted to see, would an MVP solve the problem? And they rented an MVP, and on one of the survey vessels, kind of just lashed it down with some pallets and duct tape. It was pretty impressive that it held together for the 2 weeks. And we went out and did sections up and down the river. They want to know, would this type of technology solve the problem? If so, where and when is that critical? And if not, why not? Are there tricky spots where even an MVP really wouldn't solve the problem? And maybe we should think about doing something differently. And so I'll just show you some of the data there. I don't have time to go through all of it. What I'm going to show over the next few slides is salinity sections from A to B, the same slice of water from here. This is about 20 meters water depth, 23 kilometers that way. And they're all at different days of the year, different sections, so different times of the day. And they all have the same color scale. Zero is blue, so fresh water, and then in the pinks is the ocean water. And what you'll see is over different stages of the tide, there can be wildly different structure. Here I have a smooth-ish interface, and here I have a very turbulent interface. If I look at different sections, you can see from day to day and from stage of the tide to stage of the tide, I can have a very nice, smooth, turbulent. Some other data. And this is one day where we managed to get an awful lot of sections. So the idea is maybe there are some optimal times that you can go and survey here, where there'd be survey good accuracy windows, and there might be, on the other hand, bad accuracy windows that you'd want to avoid. And so using the analysis tools that I showed you in the last few slides, let's color code these water masses in terms of the surveyor. Come on, stand. So here's a section through the middle of the channel right here, through the surge barrier. And And so there's the salinity there at one stage of the tide and the salinity at another stage of the tide. You can see it's very choppy, turbulent interface between the fresh water and the salt water. And here I have a nice, smooth, gently rolling interface. And I can color code that in a way that makes sense to a hydrographer. Here, running with an MVP, getting a cast as fast as you possibly can. So using the technology to the most of its ability, we're still getting an awful lot of red. But here, I get a big wall of green. So this particular stage of the tide, an MVP does a great job. You get good accuracy. Maybe you don't even need that much data. But this stage of the tide, with the best technology to do this job and running it at maximum rate, you're still not going to get good data. So here, all of a sudden, wow, we've just done a couple of sections up and down this river for a few days, and we were able to come away with just one good piece of advice. Don't fight the tide. And this is kind of funny. The Dutch built half of their country. They're used to fighting nature, and I was telling them not to. So the high turbulence on rising tide is almost impossible to adequately sample in some locations, even with an MVP. In some locations, an MVP might be unnecessary if you time it just right with the tide. So that's just an example of how you can use these tools and these simple visualizations to turn these dense data sets into practical advice. So next, let's jump across the ocean to my old stomping grounds in New Brunswick, St. John Harbor in particular. So here's a map. And this is a data set that I had nothing to do with. It was a complete opportunistic data set for me. But it was a study that was trying to understand why do they have to dredge so much in one part of the channel but not in another? And could we do something, change the design of the port, maybe change the flow of water a little bit so that we don't have to spend millions of dollars dredging here? And this is something that was undertaken by John Hughes Clark and a few graduate students. And what they did is over the course of these 4 different campaigns was to go out with an MVP system and go back and forth all day long over a 12.5-hour period. And each campaign, they'd get about 900 sound speed casts. And actually, it was a CTD census, so they're getting temperature and salinity casts. This little animation shows you the variation in the water over the course of the tide from, I can't remember which, I think this is from November. And this is lying. It's saying that the seabed is coming up and down to meet you, but that's not actually true. The water surface is going up and down with the world's highest tides. So I didn't have time to fix that animation. But it shows you that there's a lot of interesting things happening. The salt wedge sliding in and out of this particular channel here in Courtney Bay Channel. So how could this opportunistic data set be used to help hydrographers? It was collected for the port to understand sedimentation problems. I looked at that and I said, hey, let's see what we can see from this. Because they're surveyors and they have to go out and do pre-dredge and post-dredge surveys. Maybe we could come up with some simple advice to help them get good data. And so that's what I did. I took a cast here at the beginning of each one of these campaigns and then compared that cast to every other cast up and down that section throughout the day. So I was able to come up with this wedge. And if I take the toe of the wedge and plot that up with time, I can see how the water mass looks to me as a hydrographer. What's that doing to my soundings? And the beginning of the section with my first cast, everything's okay. But as I go to the end of my section, by the time I'm to the end, up here, the outermost beam is 4% of water depth different than what it should be. And then coming back, everything's okay again. Actually, it's quite okay. So going there and back, using one cast, I can see a variation of 4% in my depth of air. That's capturing the spatial variability. In a small window of time, maybe 25 minutes, running up and back, 4% of water depth. And I can see the next section. So there and back, turn around and run up through here, and then do another section through there. And I can see that now this cast at the beginning here, compared to the first cast of the day, is different by 2% of water depth. So there to there to there to there, that's capturing that temporal change, that same location. But I can see the spatial variability is getting smaller and smaller with each section. In fact, this section here, 8 hours into the day, from the first cast here into there, they're all in error by the same amount relative to that first cast, but the signal, the dynamic range from there to there is pretty small. That's telling me that the water is similar at that stage of the tide. So the spatial variability is at a minimum there. And I can see that for November. I see that same pattern. This the dynamic range in each of these point clouds is the spatial variability. The long-term change is due to the temporal variability. I've got these sections where there's not a lot of spatial variability. And I can see that in March again. Some stages of the tide I've got a lot of spatial variability, and some I don't. And in June I see the same thing. Well, not a lot of spatial variability compared to these problems. But I've got these survey windows. And it turns out, I didn't plot the tide up on here, that all happens to occur in a few hours after high tide. So now we have, based on just these simple graphs and thinking about it for a few hours, some advice to give to the surveyors. If you're going to survey in here and you want to get good data, go on a falling tide within 2 to 3 hours after high tide. Any other time at all, you're going to have some problems. What's also interesting, doesn't go back so well. Why is the dynamic range here so great in time, where in June there's hardly anything going on at all? I could have used that first cast of the day up and down that channel and never had any error worse than 1% or so of water depth. And the answer is in the TS plots. If I have temperature and salinity for the various different campaigns, and I plot that up, and I plot sound speed contours, I can see that in June, the river water, which is fresh, so about 5 or 6, and warm, and the ocean water, which is saltier and colder, have roughly the same speed of sound. In November, where is it? I've got cooler river water, slightly warmer ocean water, and then a dynamic range, pronounced range in salinity, but I'm crossing quite a few sound speed contours. So no matter how much I mix that water, I'm going to end up with some sound speed that's in the middle. I'm going to end up crossing an awful lot of contours. Here I can take any amount of river water, any amount of ocean water, and mix it as much as I like. You know, 1 part of this, 10 parts of that, or vice versa. And no matter what I do to it, I'll come up with the same sound speed. So this points to the idea that maybe there's a seasonal pattern here. Maybe there's an optimal time of year to go do a survey. Maybe I shouldn't go in November. Maybe I should go in June. I could have known that from the plots that I saw here, but the answer with just a little bit more thinking is in this type of plot. So this is just another way of looking at that mass of data and turning it into information that's useful to the hydrographer. So the findings from that, again, don't fight the tide. You can work with the tide. There are high accuracy survey windows when we have low spatial variability, so after high tide for 2 to 3 hours. Based on those 4 campaigns over 2 years, you're able to come up with that basic idea. The best time of year to survey, June. The worst time of year to survey, November. It might get it worse in December and January. If you remember the November TS plots crossing many, many sound speed contours. In December, the river temperature is going to drop probably faster than the ocean temperature. So this line is going to get steeper a little bit until the Bay of Fundy finally catches up there. So there might be even worse times, but we haven't sampled that. So let's jump to the last location, Portsmouth Harbor. And this was data collected in June of just this past June. And we actually got some data from the summer hydro students in 2009 before I arrived here. And we did some sections up and down the lower Piscataqua, right at the harbor mouth, back and forth. And here's a salinity section, or it's actually a temperature section, 8.5 degrees to 15.5 degrees, showing the tidal evolution for that section. And this shows you the temporal evolution of the speed of sound. So we have a I would say a well-mixed environment at some stages of the tide, and then a slightly stratified environment at other stages of the tide. So I would guess that this is probably the easier time to work in. This is probably the not so easy time to work in. And that shows up in our bias plots. Again, if I compare the first cast of the day to all of them, I plot the toe of the wedge. I come up with this blue plot showing me that as I go up and down the section, by the time I get to the end of the section, I have a little bit of error because the water is different. And then I come back, and the water is mostly the same where I just was at the beginning of the section. But if I watch that over the time, over the tidal cycle, it's getting worse and worse. So that's the temporal variability. There's the spatial variability. And what's interesting is if I take the first difference of this signal, so I compare this blue dot to that blue dot, I get this little red signal here. And that's telling me how different the water is from one cast to the next. So how good is this measurement at predicting the next measurement I'm about to take? And if it's if it's very good, that means the MVP is going to do a good job. So I have a time of the day when an MVP would work well, and a time of the day where the difference from plot to plot, from point to point, can be quite high, and the MVP system wouldn't probably get the capture the variability as well as I like. So this is another way of looking at it. This tells me that there's another survey window here. On a rising tide, it's probably the best time, even though there's a lot of spatial variability. Something like an MVP can still get the job done. On the top of the tide, it's a little choppy from cast to cast to cast. The water mass is changing quite rapidly, and I'm not capturing that. So that's another different than the findings we found for St. John, which said survey on a falling tide. Here it said survey at the bottoms of the tide. And we didn't have a full tide cycle. We only went for 6.5 hours or so. And if I look at the TS plots from that, it's a little bit different. It sure would be nice if the sound speed or the TS points lined up with the sound speed contours. We can see that that kind of happens near Memorial Bridge, not so much near the harbor mouth. And if I look at some data that Larry Ward collected in 1997 to 99, so this isn't a great bay there. He got casts up and down, just a few stations with each campaign. And plotting that on here, we see February and March crosses a lot of sound speed contours. In April, not so many. But in June, according to Larry's data, that would be the optimal time of year to survey, just like it was in St. John. That's interesting. I wonder if there's an optimal time of year to survey in every port up and down the eastern seaboard. We have some tools to start to ask questions like that and then give people advice. If you're going to go surveying up and down the coast, you might not want to do it at this time of year, So what are the findings from there? Again, the best time of year to survey was June. The summer hydro data dictated a little bit differently, but we got data towards the mouth of the harbor, and Larry didn't really get that far up to the mouth. So there might be some more to clean up and look there. It's easier to work up near the Memorial Bridge, but trickier at the harbor mouth. I mean, these are based on one day of observation. Really, we need to collect more data. And there's a survey window after low tide in June for about 3 hours. But what about the other months? We have a very small snapshot of what's going on in the Piscataqua River down at the mouth. What about the other months? And that brings me to some field work I've planned this summer. In May, we have a new corporate partner, Ocean Science, the makers of the underway CTD, and Brook Ocean, by the way. Brook Ocean is also a corporate partner. The MVP system comes to visit every year during summer hydro. This year, we're getting another tool in our tool belt, the underway CTD, and we're going to put it on the stern of the coastal surveyor. And I plan on going up and down as much as I possibly can, as much as Ben and Emily will let me, and do that to try to answer some questions. I'd like to get some tidal cycle surveys, 12.5-hour surveys, at least monthly over the summer and into the fall, and do opportunistic surveys before and after rainfall events. Talking to Larry, he seems to feel that rainfall events are bigger changes, drivers of change in the estuary than the tidal cycle. So maybe that's something we should study also. And I'd like to also look at springs versus neaps, do one survey in each and see if the findings differ. Should we be always surveying on spring tide or maybe on neap tide? So collecting a mountain of data. What do I hope to learn from all this? I want to refine some of these field procedures. Is there an optimal way to go out and collect that data? Should I always go up and down the main axis of the channel? Should I spend half a day doing cross-channel sections also? There's lots of other things that we could do. I'd like to optimize the analysis methods and some of the real-time visualizations so that you don't have to go back to the office and sit there and think about it for half an hour or an hour a day. If you could have a real-time visualization of that data that allows you to make that decision in real time, you could do this as you're surveying as opposed to spending a day beforehand collecting data like this. So why this long-term study? I mean, who would ever do this in real life? If we wanted to survey here, nobody would go out and spend months collecting oceanographic data to get their sounding accuracy from there down to there. That's an academic exercise, really, what we're doing. But what I hope to do is come up with these methods and techniques and tools to come up with the same thing that the pilots have when they're driving into harbors. They have the coast pilot that tells them, these rocks over here are dangerous on a rising tide, so you never want to berth on this side. All that sort of advice and practical stuff about harbors that varies from port to port to port is documented. And if we could do that, for surveyors, that would be pretty handy. Not for every port, not for every survey we ever do, but for the surveys like in the Port of Rotterdam, where you have to do this 13 times a year. If you can shave the survey budget by 10 or 15% by just working a little bit smarter, you could save an awful lot of money. And kind of like going to the moon. I mean, we went to the moon because we could. That was nice, maybe an academic exercise. But the trickle-down effect of all the technology that was developed to get a person on the moon has benefited us all tremendously. So an analogy would be, this is a big academic exercise to go study an estuary like I plan to this summer. But the things that come out of that, I think, are going to help all hydrographers. So I could use a bit of help. If anybody's got an ADCP, I sure would like to have one on there during the survey. Here's a temperature section to Rotterdam. And if I look at the ADCP current azimuth, strength, and reflectivity, I can see some correlations between these signals. And the ADCP, which is pinging it several times a second maybe, helps me see in between the blanks. If I'm capturing MVP casts that are 90 meters apart, I can't see the turbulence in between those. So the ADCP kind of helps me fill in the blanks a bit. I could use extra hands on deck for acquisition. If anybody wants to come out and learn how to use the underway CTD technology, I'd be happy to have you out, and there'll be some training arranged when the system arrives. And I know enough oceanography to be dangerous, so if someone knows a lot of coastal oceanography, I think Larry Ward wants to jump on board a bit. If anybody wants to pitch in a little bit to help do some interpretation of what's going on, I sure could use a hand with that. And really, if this data could help your work in any way, if we change the way I plan to do things slightly and it could benefit you, I'm happy to collaborate. So if these large data sets that come out could benefit more people, I'd be quite happy to bend my evil ways. So in summary, hopefully I've made the point that having the right tools, hardware, software, technology, can take a lot of the mystery out of refraction. Advantages, I think I've argued, to having that reconnaissance data. Instead of going in blind and working and hoping for the best, if we do a bit of prep work, we can achieve a better outcome. And I think it ultimately helps allocate resources. For example, on the NOAA vessels that have several launches, not all of those launches have an MVP. One of them might have an MVP, whereas the others might have a CTD that has to be lowered by hand. So if you could have a bit of information about where the tricky spots are, you could allocate those MVP-type resources more intelligently and end up working smarter, not harder. If I can leave you with one point, this is what I'd like to leave with. The take-home message: time spent on reconnaissance is seldom wasted. That's all I've got.
Do I say questions or one of you have to stand? Questions?
Did you look at the MVP data that we took off the Isle of Shoals over the summer? Or?
I did a little bit. It's not in this presentation. I pitched this as doing oceanographic reconnaissance, but really I sneakily just talked about estuaries. And the reason I've done that is, well, working in offshore, you've got things coming at you from every direction. And I wanted to figure out, maybe I can constrain the problem a little bit by working in a narrow channel where most of the variability is in the long axis. And we can develop tools in an easier environment. Once we've kind of got a grip on things, let's jump offshore and see what we can do in those types of environments. Should we box in a survey area? Should we run a diamond pattern? We need to play with that a little bit more, but I'm sticking to the easy case first.
Yeah. I'll take the Port of Rotterdam as an example. Can you hear me?
Yep.
You mentioned they were surveying there 13 times a year. Is there anything you can take from these surveys that you can apply for future surveys instead of taking reconnaissance as a separate thing? I mean, is there anything in there, just as an example, is there anything in their data that you can use to do the same thing?
Maybe it's my fault. I don't think I made it clear. They're surveying the seabed 13 times a year.
Right.
I went and surveyed the water mass.
No, so okay, so that's my question. Is there anything from the raw data that you can separate and use for future things?
You could take the raw data and look at how badly it does at agreeing with itself, and you have overlapping swaths. You know, at a nice stage of the tide, things line up, and at a bad stage of the tide, they won't. So that would be another way to come up with the information I found, based on how it manifests itself in the multi-beam data. That's an awful, well, it's doable. I think it's easier just to go measure the water instead of having to measure the seabed to say something about the water. Why don't we just measure the water instead? But it is one way to do it. If you didn't have those oceanographic measurements, you could look at the standard deviation grids.
Just in case you can't go out and maybe
Yeah.
you can
Yeah.
grab whatever you have.
Yeah. No, that's a good idea. That's one of the many options, I think, if we wanted to sort of reverse engineer what's going on.
Not directly related to what you did, but you mentioned St. John Harbor. They were trying to figure out why some parts was filling in and not. Did they figure something out?
I don't know. That was all sort of coming to a head as I left. You know, I wasn't involved in the project. I haven't took the data. Tom?
Thinking about like the particular like TS diagrams or just the whole thing in general. In any one of the ports that you were looking at, if you put a buoy with say 6 CTDs hanging beneath it, like maybe Jim Irish has, like one up in the harbor and one out in the harbor, did you get to the same conclusion that you got with the MVP?
Yeah. I think so. If you knew beforehand that if you expected that linear relationship from T and S, you could take a single CTD measurement.
But I mean like a time series, like put them out.
Oh,
It's
yeah,
easy
and-
to go throw something
yeah,
out there
yeah,
for a year
you
and
could
then
do
just
that.
come back and
Yeah.
get it later.
It would tell you whether you've got that right, if you're hunting for that sweet spot season to work in, yeah, that would tell you that. It wouldn't give you those fine details like working near the Memorial Bridge is easier on a falling tide. That sort of spatial granularity is the problem. You needed, I think, a spatial component to your measurements.
What can you say about your conclusions for working on a falling tide in one place and a rising tide in the other in terms of the underlying oceanographic issues?
I know enough oceanography to be dangerous. We're working in constricted channels. If you have stratified water masses flowing over constrictions, dealing with topographic constrictions and bathymetric constrictions, that can change things dramatically from port to port to port. You can have the same water masses sliding in and out of the estuaries, but what the morphology of the seabed that it's flowing through is going to change that, I think.
So you think that's a morphology issue as opposed
Could be.
to
I think that's
an
part of it.
underlying sort of water regime?
I think it's morphology is part of it, and also the nature of the estuary. I mean, estuaries are unique up and down the coast. They're wildly different. So, I mean, I think you could, with some background research, try to understand the driving principles. But if you're just a hydrographer, you can go take some measurements and come to your own conclusions without really going back that far in the literature. But I think it's helpful to do it because it helps you understand why it's changing.
So do you think you'll get to a place where you could, maybe this is what part of what Andy's asking is, if there's a strong salt wedge, it's always going to be good on the falling tide, and if there's no salt wedge, if it's just moving in and it's vertically, like this, it's always going to be good on a rising tide. Do you think you could make kind of blanket statements like that about classes of estuaries?
Sure would be nice if we could. Next year. That's down the road. It sure would be nice if we could. If we could somehow model this with some simple parameters, it might make it possible. But it's certainly something worth looking into.
And so, is there somebody else? Go ahead.
You had a follow-up? Okay. Well,
Yeah, could you go back to your plot of the data from Portsmouth Harbor, the effect on the toe of the wedge? The time series one?
yep. That one?
That's it.
Yeah.
So if you were gonna based on this plot survey in hour 1 or hour 2 or whatever, you'd want to minimize, and you could only take maybe one cast, if you didn't have an MVP. You want to minimize the variability around zero change. Is the middle of each of those humps the time corresponding? Yeah. Not the peak, but sort of halfway up.
Here.
Yeah.
That's halfway up the channel.
And,
So we took a measurement there.
and does that always correspond with halfway up the channel on those, or?
Well, it depends on how fast we were going.
I guess what I'm
Pretty
asking
complex
is,
there, but yeah, loosely speaking, yeah, that's halfway to the end of the channel.
so you could conceivably pick, there's like an ideal place and an ideal time to go and do a cast if you can only do one,
Yeah,
for the whole shoot match.
yeah, that's what this tells.
Okay.
It allows you to look at the data in that way, that you could start to decide how to work around the water mass problem instead of just blindly fighting it. This something I did mention, the days of GPS a while ago, and maybe in the not so far future, where there weren't a lot of satellites in the constellation, you could plan GPS surveys around windows of high or low dot, dilution of precision. And this sort of red plot here gives you an idea. This is a low dot time to work, and this would be a high dot time to work. It's another way of looking at that.
Instead of just solely using MVPs, if you considered using lithography profilers, just if you could just toss that in.
That's another way of looking at it. Lloyd Huff is arguing to take a bunch of AUVs and plot them in the water, let them run overnight and all day long, and come back and report the data to you. So yeah, it's the same idea. We use the same analysis techniques. We need to think about what's the best way to sample with that type of device. If it's sloshing back and forth in the water mass, freely floating, it's going to measure the same water all day long. So it may not give us the information we need.
What's your interest in expanding this application to other non-estuarine ocean habitats, such as, you mentioned you've done some work around Shoals Island. I'm thinking about the island passes in the ocean chain in Alaska, for example, where colliding water masses create really complex frontal systems and currents, and
Yeah.
it'd be great to have better maps of those locations, because they're really
Yeah.
geologically and biologically.
We could use the same tools to collect data. I would have a different interest in it at the end of the day, but that's why I'm interested in collaboration. If you're interested in looking at this data from that point of view, I'm more than happy to share it.
I was just wondering, so overall, how significant do you think the depth bias ultimately is for the case studies you did, like in terms of, you know, the acceptable accuracy of survey data?
I plot everything as percentage of water depth. Here we look at Portsmouth Harbor, and we zoom in and we see that 1% down to minus 2.5, so a dynamic range of 3.5% of water depth. That kind of frames in the worst you can expect in Portsmouth Harbor. If I jump back to Port of St. John, it's much more pronounced, on the order of 8 or 9%. Here we go. So the dynamic range here, we're looking at minus 2 to 7. So in November, we could be as bad as minus 2 and up to 7. So 9% of water depth. So this is kind of capturing the difference between the Port of St. John and Portsmouth Harbor. This, if I took one cast and ran all day long, I would have garbage data. That's not acceptable by any survey standard. On the other hand, in Portsmouth Harbor, we could probably take one cast and run all day long, and the outermost beams would have a jitter of 1 or 2%. But if we walked in a little bit, most of the rest of the data would still be okay. So we can get away with not sampling as often in that particular case, but you would be murdered in the Port of St. John. It's just you wouldn't be able to do that. You couldn't get away with it. Does that answer your question?
Yeah, thanks.
So it varies, I guess, is the answer. One more minute.
Great, well,